Let me double check that the transcript is on. It is. They can hear me. Hi. So let's continue reviewing. The last time that we talked on Monday, we went ahead and looked at Gauss Quadrature. Which is somewhere here. So again, the idea of Gauss Quadrature was to take a complicated shape and break it up into rectangles. And depending on how many rectangles you want, that'll basically dictate how difficult the problem is. So for this example, I said to use a 2-rectangle quadrature rule, where this was the rule, where I approximated x to the 4th as a linear polynomial. The reason why is what? Why did I choose this to be linear? To approximate it. Huh? Yeah, it's not that. Not necessarily. It is easier, but there's a reason specifically why we choose this to be linear. Somebody help me out. What do you mean? I mean, that's on the right track, I guess. But more mathematically, looking at this equation, maybe if we scroll up, we can see this. We did this proof the other day. We approximated f of x as a linear polynomial if we wanted to do a rule that was something like this. Why did we have to do linear? Why not quadratic? What's the method of undetermined coefficients? What does that mean? Yeah, because we're trying to find unknowns to tell us what the unknowns need to be for the exact representation of the function, the linear function. How many unknowns do I have in this expression? Now you know A and B, those are the bounds. 2. So why do you think I choose linear? Because there's only 2 unknowns. That's exactly why. If I were to do method of undetermined coefficients, which I did in this whole class last time, you see that we have an A0 term and an A1 term. On the right side, we'll have an A0 term and an A1 term. We can match the coefficients. That will ultimately give us a system of equations that we can find C1 and C2. Is that hard? Oh, it's a lot, I know. But that's the idea, that you can take a complicated function, represent it as a polynomial. So basically, let's just say we integrate A to B complicated. We will approximate that as an easy polynomial from A to B. And because we don't necessarily want to integrate that polynomial, that requires us to do some sort of, work to find the slope and the y-intercept or all the terms type of thing. So what we do instead is we force equality here to say that this is the summation of some rectangles. This is Gauss quadrature. So again, our approximation is that we have a complicated function like x to the 4th that I just showed. We represent that in theory as an easy polynomial, or you can represent that as the sum of these rectangles. And that will give you an approximation for the area. Does that make sense? Randy, does that make sense? Shafi? Nick? Yeah, if I give you something like this, I will tell you it's exact for these reasons. So then you can go ahead and derive it if you need to, if I ask you to derive it, or I tell you to use that rule. Now, we saw how complicated this was just for having 2 unknowns. If we come back to this proof, it gets really annoying. As you increase the number of unknowns, the system becomes highly nonlinear and becomes difficult to solve. So that motivates us to try to find a way to have an increased number of rectangles to get the best approximation we can without deriving it. And this motivated the next note set, where we basically had smarter people derive these equations and they put in the unknown values into a table. So if we come down, here's a table where what we see is that for, let's say we do two rectangles. This is the two rectangle. Let me highlight that actually instead of doing that. If you look at this is the two rectangles. What this shows is that if you have two rectangles, and this specific rule is something like C1 f of x1 plus C2 f of x2, those are our two rectangles. Remember, the C's are the widths of the rectangles, and the x1 is the x value where you evaluate your height of your rectangle. We can look at this table and pick out what these coefficients are. But there's a caveat. What is the thing we have to do before we can use this table? Yeah, change the bounds. If you meant transform, that's what it is. Change the bounds. To what? -1 to 1. That's correct. So if we go ahead and I give you some complicated function, from 3 to 7 of some function, before we use the table, we have to convert this to -1 to 1 of some new function, g of t, dt. Once we have that new function, we can now use the table to express the approximation of that integral. Is that okay? Thumbs ups. Okay. So how do we do that? Well, let's think about a graph. First off, if I give you bounds between a and b, the distance between those bounds is b minus a. I need that distance to be 2, right? -1 to 1 has a distance of 2. A to b is some arbitrary thing. It depends on the bounds of the integral you're trying to do. It could be from 12 to 37. I don't know, something random. We need to change that set of bounds to -1 to 1. That's one thing we have to do. Or that's the moral of the story. Not only do we need to change the width of it, what else do we have to do? We have to change the height. That's one thing we'll talk about in a second. What's the next thing? Yeah, Alexi, what you just said, you have to shift it to the left or to the right. So let's go through this step by step. Let's say I give you a function that is being integrated from 6, let's say to 10. I run out of room. Let me just make this more condensed. 6 to 10. What I first need to do is shift it over so that it's symmetric about the y-axis. So how much do I need to shift it over so it's symmetric about the y-axis, do you think? That's correct. It is 8. Let's think about y. If it's symmetric about the y-axis, what we'll see is that the midpoint of this will have to be aligned with here. Do you see that? I'm trying to draw a thicker line here. The midpoint of this will have to be aligned with the y-axis. Then you'll be symmetric about it. Is that okay? You see that? So in this example, this happens to be 8, which means I need to shift it over by 8 to the left. So now it's 0. What is 10 going to become? 2. We shifted it over by 8. What is 6 going to become? -2. Well, that makes sense. It's symmetric about the y-axis. It should be positive and negative of the same exact number. So if you think about what we just did, we found this scaling factor, not the scaling factor, this shifting factor that we called C. This was the average of the two bounds, a plus b over 2. 6 plus 10 divided by 2 is 8. That's how much we're going to shift it over by. Do you see that? Doubts? Thumbs ups? Thank you. So the next thing we have to do is take this width, which is currently what? It's currently 4. This width is currently 4. We now need to make that what? 2, -1 to 1. So what we're going to do is try to find some value. Well, rather, I want this width, b minus a. If I divide that by some factor, I want it to be 2, right? This factor's m is what we called it. So if you think about this, this would be 2 minus -2 divided by m. That whole thing needs to be equal to 2. The width has to be equal to 2. And I think we could see just by looking at this what we need to divide by to give us -1 to 1, right? We have to half it. And if you look through that math, you'll see that you'll get that m is 4 over 2, which is 2. That's our halving factor. Is that okay? So the way that we just showed that is let's just solve for m in this top equation. You would get b minus a over 2 is equal to m. So these were our two equations that are used to change the bounds from -1 to 1. And the equation that we justified this with was this. X is mt plus c. Because if you think about what we did, we took our x-axis. This was our 6 to 10. We subtracted 8, the average, to bring it to the symmetric part of the y-axis. And then we divided by m, and that gave us t. The t-axis corresponds with our table, -1 to 1. So if I rearrange this, you end up getting mt plus c. Is that okay? Barkley? Earlier? Is that okay? So, just for that equation we just had, let's scroll back up to this guy. Here. Let me go ahead and erase this because I didn't complete this. The next thing to draw is the final set of bounds, which goes from -1 to 1. And now we can use the table. And now we're in this t-axis. This is all x because we're doing this transformation. Where if you want to convert back from this equation, x is equal to mt plus c. In this problem, we found that m was 2. Those are the bounds divided by 2. And then we found that c was 8. That's what it ended up being, right? And if you were to plug in the t values, which are -1 and 1, what do we get? Well, if we do t is equal to 1, we get x is equal to 2 plus 8, we get 10. Oh, look, that was our original upper bound. If you do t is equal to -1, you get x is 2 times -1 plus 8. That gives you 6, which is our other bound. You can check if you did your math correctly because they should transform between each other. Does that make sense? Yeah? Okay, cool. Now, once you do that, you have to do one other thing. So we see in this example, I originally have this triangle that's bounded between 8 and 20, it looks like. 8 and 20. The area of that triangle is half the base times the height. So the area of this is what? Mathematicians. 72, that's correct, 72. If I change the width to go from 8 to 20, a width of 12, ultimately to a width of 2, The only way to maintain the same area is by elongating the height of the triangle. So in this example we see now, we have half the base times the height, we get the same exact area. So we can move and shift these things around however we'd like, but specifically for Gauss quadrature, we want to shift it to -1 and 1. The width changes to 2. As a consequence, that height has to go up a lot. Now the question is, where does that height come from when we're doing our math? So let's say we have the integral of f of x. We want to change x to be mt plus c. Remember that this whole thing was x. I'm just substituting in x. And now I need to multiply by what? I'm missing dx right now, right? This is what I'm missing. If you look at this bottom part, we see that dx is going to be what? M dt. So this will be m dt. This whole thing was dx. Once we do this transformation, what that allows us to do is change these bounds. They're not a to b anymore. They're now -1 to 1. And this whole function here with the m is what? That's g of t. And once you do that transformation, you can now use the tables. Does that make sense? So I give you this example here where I'm integrating some complicated function. Yeah, Andres. This is note set 24, I think. 24? I think that's right. So we have this complicated function. We want to use Gauss quadrature, but I tell you to use a 3-point Gauss quadrature, which requires us to use the table. So the first thing we need to do is transform the bounds to -1 to 1, which requires us to find that m value and that c value, the transformation. Because we said that x is equal to mt plus c. Okay, see that? So c is that shifting value. That's the average of the data points. So c will be a plus b over 2. What is that in this case? That's going to be, 1 plus 5 over 2, which is 3. Okay. Again, if you think about that 6 to 10 graph that I just showed, we looked at the average of those points and then shifted it over by that amount. That's what gave us 8. While m was taking the width, which is b minus a, and then ultimately, because we want that width to be 2, we would end up getting m as being b minus a over 2, which is 5 minus 1 over 2. That is 2. Do we see that? Doubts about this? Concerns? Okay. So that means that x will be 2t plus 3. And what is dx? 2dt. That step is the step that most people forget. Last semester, we'll see this on the practice exam, I had a problem that basically said convert the bounds. And most people forgot the dx. That's a dumb thing to forget. You have to change the multiplication factor to change that height. That's what that extra m is doing. It's changing the height of the graph to account for the fact that you're compressing it. So now that we found x and dx, we can plug that into our function. You see that? If we scroll down, we can see that we did this already. F of x will become f of mt plus c. You can see we did that here, because we found the 2 and the 3. And then m dt was dx. We've included that there. Confusion at all? Right, because if I'm doing this transformation, remember, m and c are constants, but t is just like x. It's a variable that we're going to integrate throughout. So if I take the differential of both sides of this will become dx. M is a constant, so that doesn't change. T, the differential of t is dt. And the differential of c, a constant, is 0. So dx you have to replace with mdt. If you think about u substitution, that's kind of the same type of thing, right? We solve for u in terms of x, we find du in terms of dx, and then we can replace it in our integral. It's the same exact type of thing. That makes sense? Yeah, this 2 that pops out is the change in the height. That's just the m. That's what's happening here. So depending on the width of the bounds and what your m value is, if I shrink it by this amount, I need to increase the height by the same type of amount. See that? That's what that's saying. That may answer your question? Yeah. Cool. So at this point, what we'll do is that instead of using x, we will plug in what x is and change our main variable to t. So this was x, 2t plus 3. This integral is 0.2 times x. This is x. And then this was the m dt. You see that? Again, if we look, we can see that we have x, which is this x, times 0.2. This 0.2 comes from the function, times x, which is 2t plus 3. We're substituting in that value. And then we'll multiply by m dt. Is that okay? No, it depends on the bounds. In this example, it happened to be 2 because I'm going from 1 to 5. I'm cutting a width of 4 to a width of 2. That factor is 2. But if I have a width of 20, m ends up being 10 because I need to cut it in by 10 to make it 2. Do we see this? This okay? Ebert? Okay. So now that we have this integral, this is g of t. This whole thing, including the 2, this is g of t. Now I can use the tables because I have my bounds set up correctly. So if I want to do a 3-point Gauss quadrature, I will write this as C1 g of x1 plus C2 g of x2. These are all rectangles, where we're using this new function as our height of our rectangles. Do you see that? So what we'll do is if we look at the table, let's come back up to the table, because I didn't get to show this in class that one time. If you look at the table, you can see that if you have 3 points, here's your C1, your C2, and C3. Here's your X1, your X2, and your X3. That is what we were going to use to find out our approximate area for this function g of t. What do we notice about C1, C2, and C3? In regards to, what do they add to? They add to 2 because we're going from -1 to 1. If you look at your x values, you have -0.7, 0, and +0.7. That's all within the bounds of -1 to 1. This table is only valid for -1 to 1. Do you see that? So we are approximating these rectangles with certain heights and certain widths. That conceptually makes sense. Doubts. Kevin, you okay? Anthony. That's okay. Yeah, because once we convert it to this new integral, we're going to plug in x in for t, like these constants. It's really just writing this new function. I called it t because it gets confusing if you say it's still the x-axis. I want to make it sound like we did some transformation to a new world where we have a new set of bounds, a new height, this new function. With that new function, we'll plug in those values from the table. So from the table, we have our C1, X1, C2, X2, and C3, X3. You can go ahead and plug those in. Remember that this whole thing, that's all this math right now, that is g of t, but I'm plugging in x1. And that gives me that height, or that height basically, at that location. We'll do the same thing with g of x2, the same thing with g of x3. We will add them all up, and we get 9.083, where the true value is 9.084. Pretty good. Are there any questions about this concept? Yeah, for Bensley.
Is there a function?
That I don't recommend using Gauss? Yeah. Not that I can think of off the top of my head. Gauss Quadrature is probably the best integration technique, at least out of the ones that we talk about in this class. It gives you the most accurate answer. I don't know of one where it would be not possible to do or not recommended. I'd have to think about that, but I don't believe so. Anthony.
On the exam,
No. I will be specific. The question was for the recording, do we have to follow the exact C1, X1 to infinite amount of decimal places? I'll tell you, do 3 or 4 sig figs to carry forth, because that would be annoying to do that. Dexter.
So will it be in the Gauss quadratures on the exam that we can't use the table?
Sure. That's totally possible, because we went through a 2-point Gauss quadrature in the notes that didn't involve using the table, or 1-point Gauss quadrature. You can do those equations. So it's possible. So I expect you to know how to derive them in general, and I expect you to know how to change the bounds. That type of thing's important. Jacob. Well, depending on the complexity, like a 2-point Gauss quadrature that we covered in class had 4 unknowns, C1, X1, C2, X2. We did not even derive that in class because of how complicated it is. If it's something I ask you to derive, it will be something that is way more simple than that. It'll be fair. I'm not going to have you do crazy nonlinear crap. Okay? So, any questions on integration? Okay. So we have 2 options now. I can go through the review of ODEs, which we just did last week, or I can do the exam. We're gonna try to do both, but I don't know if we'll have time to do both. Speedrun? Speedrunning's not a good idea. Exam? Let's do the exam. Now, it's nice that I don't have the answers with me, but I do have the TA's exam from last semester. And obviously, he did very well. Otherwise, he wouldn't be a TA. So he's going to be my check for the results. So, true or false? An engineer is proposing the quadrature technique below to determine the integral of a function f of x from x equals 0 to x equal b. True or false? The quadrature rule would be exact for integrating polynomials of 3rd order or less. I want you to think about it for a second. So the question then becomes, how many unknowns do we have in our quadrature rule? It's 3. What do we know, Karam? We don't know C1. We don't know X1. We don't know C2. We do know B. Yeah, it's the bounds of the integral. You have to know the bound of the integral, right? So that means if I were to do method of undetermined coefficients, how many equations do I need? 3. So I need 3 equations. If I were to do third order, that's going to be 4 equations, which means that we're going to end up assuming something about that, which will lead to inaccuracies. So if you were to go ahead and integrate, so what kind of polynomial do I want to integrate? Second order. So if I were to do a2 x squared plus a1x plus a0 dx, this will ultimately give me 3 terms with 3 variables or 3 coefficients, a2, a1, and a0. What we're going to do is plug in x1 into this, plug in b into this. We wouldn't do this. This takes way too long. And then equate the sides. So the answer is false. Only valid, or I don't say valid, only exact for polynomials of order 2 or less. Let me see that. The number of unknowns is your friend here. We know the bounds. We do not know C1, X1, and C2. That'll dictate what polynomials we have to integrate to give us the exact answer. And in this case, it ends up being 3 equations, which is a second order polynomial. Questions? Cool. A Wright-Riemann sum may overestimate or underestimate the true value of an integral. Draw pictures to explain your answer. That is true. This is true. If we were to draw a picture, what would you draw? Yeah, you could draw 2 separate pictures. It doesn't need to be one function. That's a good example, though. I'm going to do simpler than that. Let's say I just do just this for the sake of a portion of the sine wave, like you just said. So if we do a Wright-Riemann sum rule, in this example, we'll be overestimating or underestimating? Over. Remember, if I'm doing, let's say, 3 rectangles, in this example, I am overestimating the area. Now imagine I have a similar graph, but I do something that's like this. And now I do a Wright-Riemann sum rule. I'm underestimating. Do we see that? Because if I do the right side, we see in this case that I'm drawing these rectangles. Missing area. So this is true. Doubts about that? I think that's one of the easier questions on the exam. Number 3, a regression model will perfectly fit the data if the sum of the residuals is 0. Who says true? Who says false? False. Fuck. The reason it's false. Yes. That is good. Is that the sum of the residuals? That's the sum of what? The residuals squared. This was a slightly tricky question. You have to read. Why does this not mean a perfect fit? I think you said it before. What you say, Jacob? If you're not squaring, the positive and negative residuals can cancel out. So this is false. This needs to be the sum of the squares of residuals. You had the right idea, but again, words are important. Read the questions carefully. Especially this is something we've talked about in class a lot. This idea of the positive and negatives canceling each other. That's why I asked this question last semester, because we talk about it a lot. Is that okay? Okay. Number 4. This is our first actual problem on the exam. An engineer performed an experiment and measured experimental data that's presented as points in figure 1 below. A regression model given by the following equation is also shown. So I give you f of x is 20 e to the negative 0.4x. That is the regression model. That is the curve, the black line that I drew. Part A, based on the data and the provided regression model, find the sum of the squares of the residuals. I want you to spend a few minutes doing this. Go ahead and try this. I don't want you to zoom through this. I want you to practice, considering that like 3 people have taken the practice exam. Andres. Sure. We'll see. Yeah. Yes, those data points are exact. So if you want to consume it on the graph. Now you can't just look at the curve and be like, oh, that curve is equal to, you have to do something else to find the values based on the regression model. But go ahead and take a second to do that. When you get an answer, let me know. I want to come check it.
Oh, okay, okay. How much is it?
7.
Yeah, you're wrong.
No, it's fine. It's fine. I think I didn't give them a number, but I just looked to see if they were close, and they gave them full credit. They were close. Who would like more time? Okay, I'm gonna give you another 2 minutes.
You.
Yeah.
It's so drunk. Yeah.
Yeah, I got that.
Yeah, I would have been never feel it.
That doesn't have to be.
Okay, so you're saying I keep feeling it. You just gotta get it together. Oh, you don't need to feel it.
But like an apple, you just-
Bite sideways out of it. like a bite mark. Like a corn on the cob.
Yeah.
For 3, it's falling asleep early.
Go for nine.
She was sitting there like this. You want to sleep more?
Well, we probably have caffeine.
I just I saw her sitting like this.
It's a lot of explosive.
Her molecules will line up her with she's already she's
Good.
I don't know.
Marco, you feeling good? Okay, let's go ahead and do this. So the sum of the squares of the residuals is SR. That is the summation of yi minus f of xi. That whole thing squared. How many data points do we have? 3. So we have to do 3 types of sums. So let's write down our points. What's this point? That is 2, 8. The next one. Yep, and the last one, 5, 3. So, what is y1? 8 minus xi plugged into the function. What is xi? 2. So it's going to be 20e to the negative 0.4 times 2. That whole thing squared. You see that? Plus y2 is 5. That's from this point. Minus 20e to the negative 0.4 times 3.5. That's the x value. squared. And we do one more. That'll be 3 minus 20 e to the negative 0.4 times 5 squared. If you do that math, you will get SR is approximately 1.06. And if you did more sig figs, if you just got 1.06 on this part of the test, I was gave you full credit. Is that okay? So that's the equation. The sum of the squares of the residuals is SR. You know, I don't write on the equation sheet, this is the sum of the square of the residuals. You have to know, what SR means. And if I use the words for it, you have to recognize which equation that is. Questions about this? Okay, next part. A second engineer believes that a more appropriate regression model is given by the equation below. Using the least squares method, derive an expression for the coefficient A. This one gave people a lot of issues. So you have to go ahead and first off know what the least squares method is. I think when I introduced this the first time, I was like, last semester I had a student that didn't know it and they raised their hand. They said, I don't remember this. And I said, I don't know how to help you. I'm sorry. I was like, okay, cool. Thanks for letting me know. The least squares method, you know, I'm not going to say it yet. Go ahead and try it and let me know what you get an expression for A. That's what I would like, is ultimately what A is. So doing that for the video, the break, so people can get competitive.
That's what Brooks gaslighted right now.
Wait, tell me what he said.
I don't even know what he said. I mean, that's what we just said.
Did you say like something like
Well, Lewis is gaslighting himself out of the situation. She gets her glasses off. She can't see.
can't read? I'm writing right now.
I said no, you couldn't find me. Pattern with that. Residual is what?
That's what we're doing. Yeah.
No, he didn't say so. He said he does.
Yeah, I think that part.
No, you find it.
They're the same direction. She's free. Is this supposed to be like a really simple answer that just do it wrong? Oh wait, I did.
No, you can't cancel.
Oh,
Right, you can't.
right.
Oh.
Wait, so before canceling though, was it right?
I think that's right. You gotta answer. You're missing the summation, but yeah, so, right.
That's what the. Mhm. What do you do now? What in the world?
That would. Why is everything always mocking you? We're not mocking. We're mocking you calling us a lot.
So it's A over X. Yeah.
I did what everybody did on this topic. Like monitoring you like a fifth grader trying to for sure would have canceled. I literally just did. I would have gotten that wrong. Me too. I would have. I've been like, yeah, that makes sense. Yeah. You're like, wow. I totally understand.
Oh, yeah.
So two and multiply by negative one.
Right, that would be true. Yeah. You can do the next part. If you're done, do the next part, which I'll pull up on here. It's just telling you to compute it, what A is specifically for the data. So I'll write those data points down again. That was 28, 3.55. And then 5.3, I think. 5.3. So based on that expression you got for A, you can find what A is. That's the final part of this problem. You can go ahead and do that if you'd like while I'm waiting for other people.
You can't, okay, so you can't separate. Don't separate those. You can't separate those. So it's just y I over x.
No, just class over X.
Or wait, no, you plus, do a summation of it. Plus a times the summation of x. Oh, wait, well, you can't square up the x with an a row either. Yes, you can because you can't when you pull it out. So like, look, this is what, yeah, this is what you can separate the summation. You can pull the a out, so it's the summation of 1 over x squared.
Well, you don't want to do anything.
So I should be writing a over x.
Well, I mean, also the
Yeah. Oh, so then you can, so then I can get
Okay.
summation. And so that you multiply by summation.
It has to be specifically.
Well, it's,
Yeah.
so here, it's a 1/x squared.
Wait, but don't you need to find the y?
I did.
So where did it go?
It's right there.
Oh,
Okay, it's perfect. But you have an x squared too.
right, so then isn't it just y? You can't separate this back from y, so it's multiplied by
You're not multiplying. They're acting by addition for here.
right, okay.
Yes.
So,
And then you,
Yes.
then you divide it out because you have a constant of a multiplied in front of the summation.
I can't get over how big that. No, that is. It's too big.
Once you're done, well, I don't know, I'm like, I should like pay the eight, but why not buy it? Right. So now.
Okay, should we start? Should we do this? So, for this problem, the least squares method is the idea that we're going to try to minimize the sum of the squares of the residuals. So SR is a summation of yi minus f of xi squared. So I want to minimize the sum of the squares of the residuals for f of x being a over x. So I will plug that into my function. What do I have to do with SR in order to find the value of a? That minimizes SR. You have to take the partial derivative with respect to a. It wouldn't, because there's only one variable. It ends up being the same, but that's typically how we'll write it. So if we're taking the partial derivative of a series, we can take the partial derivative of the term inside the series. That will cause this 2 to come down. We have yi minus a over xi to the 1. Am I done? What am I missing? I think the derivative of the inside with respect to a, which is negative 1 over xi. And that whole thing has to be equal to 0. What things can I cancel now if I wanted to? The 2 and the negative 1. This would be the summation of yi minus a over xi, 1 over xi, is equal to 0. Now what I want to do is try to solve for a. So I'm going to distribute that xi in. This will be yi over xi minus a over xi squared. That whole thing is equal to 0. Now what I want to do is separate the series out. This is the summation of yi over xi minus the summation of a over xi squared. And now I can go ahead and solve for a. The summation of yi over xi is equal to the summation of a over xi squared. What can I do with that a? Am I missing what? I canceled that. Remember, it's a negative 1 and the whole thing's equal to 0. I just ignored it. Just like the 2. If you kept it, don't distribute it, you'd still get the same answer. I can take that a out of the series, right? This will be the summation of yi over xi is equal to a, the summation of 1 over xi squared. I cannot just cancel things inside their respective series. I can't say, oh, there's an xi here and an xi there. I can cancel them. You cannot do that. It doesn't work because you're summing things. If I had 1 plus 2 plus 3 equals 1 squared plus 2 squared plus 3 squared, could I just cancel terms? Not really. You can't do that. So what I have to do is instead solve for a by dividing by this. You get that the summation of yi over xi divided by the summation of 1 over xi squared, that whole thing is equal to a. Again, a little bit of algebra towards the end, but the process, once you know it, should not be that difficult. It should be on repetition. It should be on repeat in your brain. Find SR, take the partial derivative, solve for the unknown constant. So what we need to do now is sum yi over xi. Let's look at our data points. Oops. Stop it. Better. So the summation of y over xi will be the summation of 8 over 2 plus 5 over 3.5 plus 3 over 5. That ends up being 6.0286, I think, based on at least Morrow's work. And then the summation of 1 over xi squared is the denominator. That's 1 over 2 squared, 1 over 3.5 squared, plus 1 over 5 squared. That whole thing is 0.3716, which means that A is equal to the 6.0286 divided by 0.3716. That ends up being approximately 16.2. What is a way you think you can check your work to make sure that you're correct? Because right now I'm saying that f of x is a over x. How do you think I can check my work? Plug in the x values from the graph and see if you get close. So if you plug in 2 into that graph, you'll get approximately 8. If you plug in 3.5 into that graph, 16 divided by 3.5 is approximately 5. You know, you do it in your calculator. 16 divided by 5 is approximately 3. It makes sense, right? We're trying to regress to those 3 data points. So it should try to go through those data points. You should get answers that are pretty close. That makes sense. That's the nonlinear regression problem on the test. Is there any questions about that? Okay, moving on to integration. Engineers are interested in the integral below. Estimate the integral using the composite trapezoidal rule with 3 trapezoids. So go ahead and try this. I'm going to give you like a few minutes to do this. Andres. No, I'm recording this. Yep.
said the same thing earlier.
Feel ready for it? Now you understand it? Finally here. How's that class going?
Awful.
I mean, it's good, but not good.
No, it's not. What does that mean? Pretty sure you said you wanted you stayed that class yesterday after you submitting the project. I don't think that's in here.
Well, no, I mean, of like academic. I mean, like the actual, reading, hearing, I don't know, whatever.
Too much time on them.
The will to do practice tests like 5 times.
Exactly. That's what I'm saying.
Yeah, you're pretty that too. I guess.
She's like afraid if she gets below an A plus, like die or something.
No.
That's what it seems like.
Almost. Yeah, 100%. No, 0%. For the sake of time, I am going to start this now, this trapezoidal one, because we've done trapezoidal rule before. At least you have. So again, if you are confused about the trapezoidal rule, you can go ahead and draw a picture of any arbitrary function. It doesn't matter what the function is. That kind of helps me visualize in my head what I need to do. So if I draw some random function, and I'm going to go from 2 to 8, and I said if I have 3 trapezoids, what is going to be the width of each of those trapezoids? 2. And again, on your equation sheet, you have delta x is b minus a over n, which will be 8 minus 2 over 3. That's 6 over 3, which is 2. Did I get that wrong? Did I say something wrong? Okay. So basically, you'll have one trapezoid. I might make this graph more exaggerated so we can actually see it. Oops. Four, 6, and 8. Those should be equal in width. So here's one trapezoid, here's another trapezoid, and here's a third trapezoid. We want to find the areas of each of those trapezoids. And I do give you the general equation for trapezoidal rule on the equation sheet. But we know that the area of one trapezoid is 1/2 the height, or the width, times f of x0 plus f of x1. It's the average of the bases divided by 2. So the average is the base is sum divided by 2, multiplied by the width, right? So if we were to sum this up, this would be A total will be 1/2 delta x times f of 2 plus f of 4. That's the first trapezoid. 1/2 delta x. F of what plus f of what? That's the second one. Markley, what's the second one? No, don't tell me. Tell me in terms of f. F of what? F of 4 plus f of 6 plus 1/2 delta x, f of 6 plus f of 8. Where your f function, if I do f of 2, for example, that's going to be 2 times the natural log of 2. Because that's the function that I'm integrating. Do you see that? If you go through the algebra, you get this to be 18.25 roughly, something like that. That ends up being the approximation for your integral. Yes. Yes, you do. Where you actually add up the bounds and then twice the inner points. That's on the formula sheet. Second question, using 2-point Gauss quadrature, estimate the integral. Do not change the integration bounds. So I'm going to go down to the formula sheet to show you. This is on the formula sheet. I tell you what the 2-point Gauss quadrature terms are. You don't need to derive them. So based on those terms, you can find what the integral is, approximately. But you have to know how to do the quadrature rule. I think I actually give it on here. It's here. So this problem, you'd have C1 f of x1 plus C2 f of x2. This is more of an algebra type of thing because I give you C1 and C2. I give you x1 and x2. You can plug them in to the function and then get your approximation. What do you think that approximation, your answer, should be close to? 18. There are people on the exam last semester that gave me an answer of 18 for the first one and like 42 for the second. There has to be some recognition. Do not just be a monkey and plug and chug. You have to think and be like, okay, does my answer match the previous one? It doesn't, or not close. That means you screwed up somewhere. Have that recognition. You have to make engineering decisions in the real world to determine if you're right or wrong. That's what this is showing you. You should get the same answer or close to it. It won't be exactly the same answer because trapezoidal rule isn't the most accurate. But that's what we need to do.
What kind of error?
What do you mean, between the two?
Yeah, so like if we're trying to check our own answer.
I mean, you should get around 18. You know, if you get 19 or 17, maybe it's like, okay, the trapezoidal rule wasn't bad, you know, like, or it wasn't good.
Yeah.
So that's why it's off. But I'm going to ask you to do the integral for real in a second. That you'll get the actual answer, and that should match well with everything that you approximate, right? So I'll leave this on the sheet for you to try. Huh? You got? Good? Okay. And remember, the function was 2ln x, so we're integrating from 2 to 8. I gave you these in the equation sheet. Again, you have to have the intuition to go and find them in the equation sheet. I think a good way to be organized with this problem is just to compute x1, have that number, compute x2, have that number. Then you'll plug those numbers into the function. I think that that's just the easiest way of doing it. Hmm? because this is mostly algebra, I'm just going to do the math on this because it's not that hard of a problem. C1 and C2 is B minus A over 2. That would be 8 minus 2 over 2. That is 3. Then for this, we want to plug in B minus A. So 8 minus 2 over this square root term plus 8 plus 2 over 2. That ultimately gives us 3.267. 9. And then we will do the same thing here. Oops. That ends up being 6.7321. Where is the midpoint in this graph? Between 2 and 8, what's the midpoint? 5. And our two rectangles will be based on heights, one to the left of the midpoint. You can see that we have B plus A over 2. That's 5. Then you would subtract this number. I say subtract because of the negative sign in the denominator. So this should be a number smaller than 5. We got 3.2. This other one is the same mean, but now we have a positive version of that number. It should be greater than 5. We're calculating the heights of these rectangles on each side of the center. Do we believe that? Does that make sense? So what you'll do is say that your math will be 3 C1 times F of 3.2679 plus C2, which is also 3 times F of 6.7321. You will plug 3.26 into this expression. You will ultimately get 18.55. Okay, it's 18, roughly. We're on track. Our math is working out. Do we believe that? Do we believe that? That makes sense. Questions? Okay. Okay, so we have this integral now. I'll just rewrite it, 2 to 8, 2 on x dx. This says rewrite the integrals such that the Gauss Quadrature tables provided in the equation sheet may be leveraged. You do not need to evaluate the integral. Yes, that just means to change the bounds and rewrite this f of t, which is 2 ln x, as g of t. So go ahead and spend a few minutes on that. But our goal, based on what you just said, is to convert the bounds to -1 to 1. So spend a couple minutes on that. If I need more time, this one should be pretty fast. These are in the equation sheet. You do not need to memorize these. I give you what M and C are in the equation sheet. If you look, C, again, was the average of the points of the bounds. This was B plus A over 2. So this is 2 plus 8 over 2. That is going to be 5. And then M was the width, and we half that. So that's 8 minus 2 over 2 is 3 is equal to M. And we know that X is equal to MT plus C. So X is equal to 3T plus 5. Do we buy that so far? Okay. So that means that I will plug into my function from -1 to 1 2ln of 3t plus 5 times dt. Did I mess up? Where did I mess up? I forgot to add or include the m, because if you take dx, this would be 3dt. That needs an extra value of 3 there. I would say half the class last semester forgot that 3.
Should that be inside?
No, because dx is not inside the log. Okay? Last question, what's the true value of the integral? So you have to actually know how to integrate this. How would you integrate this, do you think? This is by parts. That's correct. That's the sole reason I included a 2, to jog people's memory that I have 2 functions multiplied by each other. You can still do it without the 2, but people don't think of dx as being a function, or 1 dx as being a function. Huh? So we want to leverage for integration by parts, our little acronym. In this case, there's really only one function anyway that you can assign u to in general. Again, you can think about your final answer. If it doesn't match something near 18, you must have messed up, because your first 2 answers were 18.
We're all not a little less than that. Not 7.3.
Why not 14.77? So is the integration method. It's skipping doing the integration method. You just remembered that.
Anybody get it yet? Good.
That's sorry.
Figured out? Okay. Let's try this. This is integration by parts. What is u? What is du? 1 over x. We could make, yeah, I mean, this is fine the way that we have it. If you want, you could also do the integral of 2 to the 8 ln x dx if you'd like. Or do it either way. What is dv? Yeah, if I leave it in the original way, this would end up being 2 dx. What's v? 2x. So our integral will be, oh, why did I put a dx there? Sorry, that's wrong. Ln x. This is dx. This will be uv. So that's going to be 2x ln x integrated from 2 to 8 minus the integral of v du, which is 2x times 1 over x dx. This is also integrated from 2 to 8. 2x ln x, 2 to the 8, minus the integral of what? 2 dx. Right? X times 1 over x is simply 1. So we'll plug in our bounds. Oh, we'll integrate this first, I guess. 2x ln x from 2 to the 8 minus 2x from 2 to 8. This will be 16 ln 8 minus 4 ln 2 minus 16 minus 4. Did I do that right? Probably. That's funny. You should get 18.49 or something like that. That ends up being a true value of your integral. People buy that. Did I do that right? Yeah. Nolan. Yeah. This. Yeah, rewrite the integral. You don't need to evaluate it. So just to rewrite it. Is that okay? No. Nope. Evaluate the original integral, which I give you below. It's this integral. That's the integration part of the exam. Questions about it? Okay. Last part, differential equations. So this first part, I said find the true value of x is 0.5. Let's do this together because it's going to take a while in general for you to do this, and we don't really have the time. So Our differential equation is x double dot minus 3x dot is negative 5 e to the negative 2t. If I want to find the true solution, what do I have to find first? I need to find the homogeneous solution and the particular. So let's start with the homogeneous. That will be x double dot minus 3x dot is equal to 0. I can assume a solution. What solution should I assume? Yeah, we'll assume that x is c e to the lambda t. We can take the derivatives of that with respect to t. Do we believe that? We assume c e to the lambda t. We've seen in class that that is a great assumption for homogeneous equations. Yes.
What is our assumption?
What do you mean?
If our forcing, like,
For homogeneous, it doesn't matter because the forcing goes away.
right.
So for homogeneous, the question was, what do you do if the forcing function is something like a trig function? Well, the homogeneous is still 0. It's the same thing regardless. Yeah, I would always assume the c e to the lambda t for a homogeneous. Question? Yeah. Yeah, I have it in the formula sheet. So let's plug these guys in. This will be c lambda squared e to the lambda t minus 3c lambda e to the lambda t is equal to 0. What do we get here? What can cancel? Let me make sure I wrote this problem down right. Yeah. So we get lambda squared minus 3 lambda is equal to 0. This is where a lot of people messed up last semester. This exact part. What is the solution to this? 0 is one of them. That's correct. What people commonly did is they would just cancel out a lambda and do that, which is not correct. In algebra, you just can't eliminate your variable like that. You lose a root. Remember, for a quadratic type of equation, which this is, lambda squared, you have to have two solutions. And a lot of people only included one last semester. So what you can do is factor out a lambda if you want. You can also do quadratic formula. That also works if you want to spend that time. But you will get two roots. Lambda is equal to 0, and lambda is equal to 3. Are there any questions about that? So we assumed the solution, took derivatives, plugged it in, solved for lambda. And again, you can't just divide by lambda here. A lot of people forgot that lambda. They ended up getting the wrong solution because they forgot, the 0. So what is our homogeneous solution? We have two roots. You're on the right track. You said C. That's a good start. That's exactly right. Yeah. Except you want to differentiate those constants. They're not the same constant. We have two roots that are each solutions. We will sum those solutions. This will give us C1 e to the 0t plus C2 e to the 3t. This ends up being C1 plus C2 e to the 3t is our homogeneous solution. Jacob. Yes. What is the caveat, though? What if I had lambda is 3 and lambda is also 3? They're repeated. What changes? Well, no, it's not that. Remember, you can't have roots that are linearly dependent on each other. So if I had a repeated root, this is off topic, but assume that you had lambda is 3 and lambda is 3. Our homogeneous would be C1 e to the 3t plus, I can't do C2 e to the 3t. C1t e to, or C2 t e to the 3t. That t pops up if you have any sort of repeated root. That's not just from the homogeneous, but if it becomes repeating in the particular, you have to include that extra factor of t. Or x, depending on the problem. Kevin. If they're repeated, you have to do that. In this problem, you don't have to because they're 0 and 3. They're not repeated. You don't have to do that for this problem. But in another problem where you have repeated roots, yeah, you have to remember to do that. On, I can't hear. Guys, 2 seconds. What? Sure, why not? It's so needy. Like, oh, I need to know what's on the exam. Give it to me. It could be anything. Give you a 6th order differential equation. I don't care. Obviously, I'm joking, Sydney. Deep breath. I'm kidding. So, I talk about this in the note set. Make sure you're reviewing the note set. So, that is our homogeneous. Now we have to do the particular. Which will include the forcing function now. So it'll be x double dot minus 3x dot is negative 5 e to the minus 2t. We have to assume a solution for x. If you don't remember what to assume, it's on the formula sheet. If you scroll down, the differential to ODEs, I gave you here that if the forcing function is e to the ax, your particular is a e to the ax, that's what you want to assume as your solution. Do we see that? Because in our situation, we have a forcing function that's e to the ax. The coefficient in the front doesn't matter. It's the form of the forcing function. Our particular will be some coefficient times e to that same exponent. So that means that we will assume that our x is a e to the what? Negative 2t. Do we see that? Now we'll take derivatives and repeat the process. X dot is negative 2a e to the negative 2t. We're taking the derivative of the exponential. The negative 2 comes down. We will do that again. That will give us 4a e to the minus 2t. And that will give us all of our derivatives that we can use to plug into our equation. Do we believe this? Are there concerns about this? You should expect to solve some sort of differential equation on your exam. Yes.
On the equation sheet, what should the E J equals A equals 5?
Oh, we're not going to worry about that. That was something I talked about last semester. I don't remember if we talked about it this semester. So I might remove it from the formula sheet. Don't worry about it. So let's plug those guys in now. This will be 4ae to the minus 2t minus 3 negative 2a to the minus 2t. This whole thing equals negative 5 e to the minus 2t. Okay. All the e to the minus 2t's cancel, which is expected. This will be 4a plus 6a is equal to -5. Do we believe that? Markley, is that okay? So what's A? Oops. That's correct. A is -0.5. That means that our particular solution will be -0.5 e to the minus 2t. So our total solution ends up being the sum of those. So C1 plus C2 e to the minus 3t minus 0.5 e to the minus 2t. How do we find C1 and C2? The initial condition. So we come back up, I gave you those. X of 0 is 2.5. T of 0. Oh, X of 0, sorry. X of 0 is 2.5, and X dot of 0 was 4. So we could take the derivative of this, because we're going to have to do the second initial condition. Derivative of C1, 0. The next term, negative 3C2. The last term, plus e to the minus 2t. So we can find C2 right away. This final equation just allows us to find C2. So if we were to do 0, and plug in 0 for t, oops, that'll be negative 3C2 plus 1. We'll end up getting that C2 is a third. Assuming I did that right. Oh, it's 3t. Sorry, it's 3t. That's correct. So we get that C2 is equal to... Oh, duh. What am I doing? Sorry. When we plug in that initial condition, this should be equal to 4 based on that. So now we get that C2 is equal to 1. If we plug 0 into our X, that will give us C1 plus C2 minus a half is equal to 2.5. C1 plus C2 minus a half is 2.5. So we get C1 plus C2 is equal to 3. And we just found C2, which means that C1 is equal to 2. Again, assuming I didn't mess that up. And then you have your differential equation, because you found C1 and C2. The question was asking what is the value of the differential equation at some time at a half. So you'd have to plug in a half into that expression to get the value. Now, this is the only time the TA got points off is that he forgot to do that, so I don't have that answer in front of me. I know, it's fired, seriously. So X total ends up being C1 plus C2 is 1, e to the 3t, minus 0.5 e to the minus 2t. That's our answer. That was a big question on the test. That was 12 points. You have to know how to do this type of thing in general. Is that okay? Questions about that, Nick?
On the test, forcing functions.
Can be either. So, continuing. This part we didn't discuss, so we're not going to do it. It is extra credit on the final, but I'm going to let you guys work that out on your own, so you deserve that extra credit. Once you do decouple, actually, this doesn't work either for the decoupled. It gets a little bit more complicated, so we can't do that either. There is Euler's method on the test, but not for decoupled second order because it's a little bit more complicated. We had some extra credit on here where I said put the steps of LU decomposition in order. This was an all or nothing extra credit. What are two root finding techniques? Interruption, bisection. What's the binary number? So you would convert that to base 10. Again, I'm testing you on things that you've seen before in the class. This is why it's extra credit. This one was, what's the first derivative of the function? Because my class last semester couldn't take derivatives, so I kept asking derivative questions. Colby. 8 points. It was 8 points extra credit. I think for your test, it's also like 8 points.